like a general strategy for the idea of a line integral?
Yeah.
Okay,
Sure.
so general strategy. Okay, first things first. Like, okay, I hope you've got an f and a curve, right? Okay, so if I've got a vector field and some curve C with orientation, right? Okay, and then just like, hey, how do you execute a line integral on this, or what's a good idea? So it doesn't matter if the f is given in terms of like, if it's p comma q, right? P being a function of x and y, and q also being a function of x and y.
Point to point.
Or maybe even p, q, and r, right? Three-dimensional would also be fine here. I mean, this and pi, oops, put the vector out of the wrong thing, plus qj, like, these are the same thing written in different ways. This wouldn't affect my decision on how I'm going to start trying to do the line integral or what I'm going to do at all, right? This is just separate notation. I'm going to take whatever they give me. If I'm more comfortable with one notation or the other, I'm just going to convert to that one, right? Like, personally, I do dot products best in this notation. So I'm going to convert to this notation basically all the time. Okay, so notation, move to whichever one you're comfy with. On the curve, well, you have a couple of tools, right, for calculating line integrals. You can either try to apply the fundamental theorem of line integrals, or you can parameterize and use this, right? Like, okay, I've got two strategies. I'm going to either do the fundamental theorem, or I'm going to take R, take C, think about it as R of T or whatever, or theta or what have you. And then I'm going to do this integral from A to B of F evaluated at R of T, dotted with R prime of T dt, right? So this guy's like my go-to that'll do whatever, right? This will do all my line integrals as long as I can parameterize the curve. So if I can get a parameterization, I'm going to move to this. The fundamental theorem, what's that consist of?
Finding the gradient.
Yeah, I need to think about a gradient, right? The fundamental theorem says basically the same thing it did in Calc 1, right? If you integrate a derivative, you get the antiderivative evaluated from the endpoints. That's really chill if I can find one, right? So what I want to think about is I want to wonder, really, is the vector field I have equal to the gradient of some function f? If it is, then I don't have to worry about parameterizing the curve, right? So if you have a messy curve, or if they didn't give you all of a curve, right, that's suggesting to go this way. What I would recommend in terms of an actual honest-to-God strategy is spend a couple of minutes figuring out, is this the gradient of something?
Can we do an example of using the fundamental theorem?
Yeah, absolutely.
Because I think I have the
okay, so you've got this
parameter
down, I hope.
pretty close. At least.
Okay. And then this one's a little bit confusing still?
Mm-hmm.
Okay, so we'll find an example for this one in a second. But the idea is the same idea as kind of your usual Calc 2 approach, right? Is this an integral I know, right? Or do I have to go someplace messier? Table, back of the book, Wolfram Alpha, nasty, horrible, like, trig sub techniques or whatever, right? Basic thing, good. Slightly messier thing, less good. Cool.